This example, merging, will show us how to use another technique to solve the problem. That is partitioning. The problem is simple. We simply want to merge two non-decreasing arrays, A and B, into another non-decreasing array. Just think about merge sort on a sequential machine. We have to merge the sorted sublists pair by pair, right? And this problem is about how to merge a pair of sorted sublists. To simplify the description of the algorithm, we assume that first the elements of A and B are pairwise distinct, all right? And furthermore, we assume that n equals m. Well, at least they are about the same size, so no big deal. And also we assume that for the sake of simplicity, both log n and n over log n are integers. Because later on we're going to make partitions according to these sizes. So we assume that they are all integers. Well, even if they're not integers, there's no big deal. So the partitioning paradigm is this. If we have P processors, we can first make a partition. Assign each processor a small job of size n over P. And the actual work is done in parallel on each processor by some normal algorithm, or say serial algorithm. Okay. We know that on a sequential machine, it takes a linear time to merge them, right? Every time we just compare a pair of elements from A and from B and copy the smaller one into C. And how can we get it done in parallel? Well, each element has a unique position in C, right? And if we know their positions, we can assign all of them into their final positions in one round, right? That is parallel. Okay, so now the question is, how can we get their positions? That is, we turn the original merging problem into a ranking problem. The rank is defined as the following. We say rank of J A equals I. It means that the position of B of J, that's the J's element in B, the position of this one in A is right after A of I. It's between A of I and A of I plus 1. So we denote it by the rank of B of J in A. Okay, if that value is I, it means that the position of this element in A is right after A of I. And that is the basic definition, and these two are the definition for the boundary conditions. And if this B of J is smaller than the smallest element in A, we define its rank to be 0. And if it's larger than the largest element in A, we define the rank to be n. All right. So the ranking problem is that first, for every element in A, we're supposed to find their positions in B. And for every element in B, we're trying to find their positions in A. Okay? And we claim that if this one is solved, then the merging problem can be solved. Claim that given the solution to the ranking problem, the merging problem can be solved in a constant time and a linear workload. But how? If we know the position of A of I in B, then what is its final position in C? First of all, there must be that many B elements stored before A of I, right? And secondly, from A of 1 to A of I minus 1, they must be placed before A of I, right? So what is the position for A of I? That's the rank of IB plus what? Plus I minus 1 plus 1, right? And it's the same thing for the elements in B. So here we go. For each A of I, its final position is the rank of IB plus I. That's I minus 1 plus 1. It can be simplified as just I, right? So this is the final position for A of I in C. And for the very same reason, this is the final position of B of I in C. So clearly there are only 2 rungs, so the runtime is a constant. And each element is assigned once, so the workload is linear. It's big O of n, right? Now let's check out a specific case. Say we have 8 numbers. There are 4 numbers in A and 4 numbers in B, and we're supposed to merge them into C. Alright? So let's first try to calculate the rank of elements A in B and the rank of elements B in A. Alright? So what is the rank of 11? 11 is smaller than the smallest number in B, and therefore by definition its rank is 0. And so is this 12, right? 12 is smaller than 13, so it's another 0. 15 is between 14 and 16, right? And by definition its rank should be what? Should be 2, right? It's supposed to be placed after the second element in B. Okay, and how about 17? That's 3, right? 17 is after 16, so this rank is 3. Now the other way around. What is the rank of 13? 13 is supposed to be placed after 12, right? So the rank of 13 in A is 2. So what about 14? Another 2, right? And how about 16? It's here, so it's 3. How about 18? 18 is larger than the largest number in A, and therefore, by definition, this is just n. This is 4. Okay? Now, according to these ranks, so what is the final position for this 11? 1, right? How do we know? It's supposed to be its rank plus its own index. That's 0 plus 1 is 1. And for 12, this is 0 plus 2. And for 15, it's going to be 2 plus 3. That's 5. Alright? And so for 17, this is 3 plus 4. That gives 7. You know how to calculate the positions for the elements in B, right? So this is 2 plus 1. That gives 3. And this is 2 plus 2 is 4. For 16, we have 3 plus 3. That gives 6. And 18 is 4 plus 4. The position is 8. Okay, now, how are we supposed to get these ranks? Well, first, how about binary search? It's very simple. Okay, within one Pardo, for each element in A, let's call binary search to find its position in B in parallel. And so for elements in B, alright? And the runtime is what? Log n, right? But the workload is n log n, because binary search is done to each element. So comparing to the sequential algorithm, the runtime is better, but the workload is worse. So not good enough. Alright, then how about simple serial ranking? So starting from I and j both being 0, and we compare the corresponding elements of A and B and update their ranks according to the result of comparisons. Well, since we have I plus 1 and j plus 1 here, we must add A of n plus 1 and B of n plus 1 as the sentinels, right? We must assign a very big number to them to avoid segmentation faults. So the workload is reduced. It's reduced to linear, right? It's big O of n plus m, but it looks just about the same as the sequential merging. So the time is also linear, right? Still not good. So a smarter solution is parallel ranking. Is to do a smarter partitioning. Let's assume that n equals m and we add the two actual numbers as the largest numbers, larger than the largest numbers. And we want to have an algorithm that runs in log n time with the workload no more than big O of n. Alright? Now think about this. How many processors must we have? It will be n over log n, right? Now let's divide the set into p parts. Do the partitioning with n over log n processors. Here we are supposed to part do the selections. We should select p elements from A and from B with a jumping distance of log n. So we select the first one and then jump over log n elements to take the next one, and so on and so forth. Then compute the rank for each selected element. For example, say we have 16 numbers in A and in B, and these are the selected numbers. And then we may call binary search to get the ranks of A in B and B in A, and then do the actual ranking for these sub-problems. Okay, and these are the smaller sized sub-problems. So how many sub-problems we may have? In the worst case, 2p, right? And the size of each sub-problem must be no more than what? Log n, right? So here we're going to have at most 2p smaller sized problems, and the size is no more than log n. So what is the runtime of this part? It takes 2 rounds, right, to select the elements. And to compute the rank, we call binary search for each element. It takes log n for each element, right? So the runtime is log n, correct? And how about the workload? There are p processors. Each takes log n time. So it's altogether p times log n, which is just big O of n. And how about the ranking part? Let's just do simple linear ranking for each subproblem. So the runtime will be big O of the size, which is just big O of log n. And the workload, since there are 2p processors with log n work for each, so it's again p times log n, which is big O of n. And therefore, the overall performance is what? That the runtime is big O of log n and the total workload is big O of n. So the workload is the same as the sequential algorithm and the time is saved. And here we use exactly n over log n processors. What will happen if we have more or less processors? How will this p affect our runtime and workload? Think about it after the class, okay?